Hello, this is Mr. Pruitt, and today I'm going to be talking about fundamental forces in nuclear decay. As we talk today, we're going to be talking about basic things that are needed to build a universe, and then we're also going to be talking about how atoms, especially radioactive isotopes, break down. Let's start with the idea that there's fundamental forces. The cosmologists, these are scientists that study the universe, tell us that only four forces have to be present to create all the matter and energy in our universe. These three forces are gravity, the electromagnetic force, the nuclear weak force, and the nuclear strong force. Now, these forces can be divided up into what we call strong forces and weak forces. And there are two strong forces and there are two weak forces. We're going to start by talking about the strong forces. The first strong force is what we call the electromagnetic force. It's responsible for binding very small particles together over relatively vast distances. And when I say relatively, you got to remember that when you're talking about a particle the size of a proton or an electron, that centimeters could seem almost an infinity away. So these are forces that can bind together these very small particles over very large distances, at least in relative terms. What the EM force does is it holds complete atoms together. It holds the electrons in their shells to the nucleus. It binds it together, and these are also responsible for chemical bonding between different atoms and elements. The second strong force is the nuclear strong force. The nuclear strong force is responsible for holding the nucleus of the atom together. If you consider what we know about the nucleus, that it's made up of only protons and neutrons, that's a lot of positive charge all in one place. Well, in our studies of electrostatics, we learned that like charges repel each other. And so we have a whole bunch of positive charges of the same charge located in one very small area. And so from what we know about the electromagnetic force, these particles should be scattering and trying to get away from each other. But the nuclear strong force prevents the repulsive force, electromagnetic force, from causing the protons to scatter. Now, this only works over relatively short distances, and again, when we're talking about relatively short, we're limiting it basically to the size of a nucleus. Our weak forces are gravity, and most people say, Mr. Pruitt, gravity is not a weak force. Gravity holds us to the earth, and we can't escape it without a lot of help. Well, from a big universe perspective, gravity is a weak force because it only has effects that are appreciable, that are really noticeable when there's large, massive bodies. Okay, you know, if you go back and you think about the blanket analogy for how Einstein defined gravitational wells as being basically like massive objects and sitting in a really big blanket of space-time, and that the dents they make are what causes gravitational attraction. Then you have to think about the fact that gravity is really very weak, because it only involves the only time that it's really appreciable is when you have really large bodies, like planetary-sized bodies, involved. Now, what you'd need to think about as far as what gravity does, gravity binds large bodies together. It holds together our sun. It holds together the planets. It holds together our solar system and keeps it all bound together that way. Gravity binds our galaxy, and there's attraction between galaxies. So it is a big force, but it is considered to be weak in comparison to the nuclear strong force and the electromagnetic force. The nuclear weak force is our fourth fundamental force, and it's responsible for nuclear decays and nuclear fusion reactions. Now, nuclear decay is a process by which the nuclei of atoms are broken down into different elements. Okay, Generically, it looks something like this picture over here, where we have some type of radioactive atom or isotope, usually some type of instability like we would find in an isotope, and it spontaneously decays. It releases some type of a particle, and it releases some energy as well. And that's our basic idea of what occurs in a nuclear decay, which is the cause of radiation and radioactive elements. Now, remember that nuclear decay is regulated by the weak nuclear force. That must be important because it was in the previous slide as well. So remember that this is all regulated by this one nuclear force. And the other thing you need to know is that there's three types of nuclear decay. There's what we call alpha decay, a second type called beta decay, and a third type called gamma. Now, alpha decay is a process in which an unstable nucleus, usually an isotope, releases an alpha particle. Okay. Now, an alpha particle is really just a fancy name for a helium nucleus. It's a particle that has 2 protons and 2 neutrons and has a mass of 4. Okay. When alpha decay occurs, we get a couple of things. We get what they call a daughter nucleus, which is the smaller, more stable nucleus that you see here. You get an alpha particle, which is that helium nucleus that breaks off, and then we also get we also radiate out some energy. The second type of decay you need to know about is what we call beta decay. Beta decay occurs when we have an unstable nucleus that releases an electron, also called a beta particle, and an antineutrino from the nucleus, and then the nucleus itself gains a proton. Okay, so in beta decay, one of the thing that most people wonder about is where did the electron come from? Because what we're taught is that there are no electrons within the nucleus. Well, the electron comes down from the breakdown of a neutron. And if you go back and you remember when we taught in chemistry class, when you were taught about atomic mass, you were told that basically protons and neutrons had the same atomic mass, but that neutrons were slightly heavier than a proton. Well, that difference in mass can be largely made up for in the mass of an electron. And so what happens here in our beta decay is that one of these neutrons spontaneously breaks down, and it throws the electron out of the nucleus. And because there's no negative charge to create a neutral particle anymore, now there's another positive particle in there of slightly less mass that is a proton. So the nucleus gains a proton, and an electron is thrown out, and then also another particle is thrown out called an antineutrino. The antineutrino is really just a way for us to account for some energy that's being released from the nucleus. Okay. Now, you do need to know that the products of beta decay are a nucleus of a new element. That we're going to get a different element because there's an additional proton in the nucleus. There's a beta particle, which is, as you recall, an electron, and then some energy. Our last type of decay that we look at is what we call gamma decay. Now, in gamma decay, the nucleus changes from a high energy state to a low energy state. Now, it's not actually we're not going to get a daughter nucleus. We're not going to get something new. We're not going to change elements because there's not going to be any change in the number of protons in the nucleus. All it's going to do is it's going to change its energy state from high to low. All right, and the way it's going to do that is it's going to emit some gamma radiation, basically in the form of photons. Remember, those are those little massless particles of light that we talked about when we were talking about Young's double slit experiment, and then when we talked about when we came back and we started talking about the photoelectric effect. So these little photons are the gamma rays that are being thrown off. Now, you do need to remember that gamma rays dangerous. Gamma rays kill you. They don't turn you into Hulks. Okay. Now, you need to know that the products of gamma decay are basically gamma rays and a lower energy nucleus, and that there's no change in what it is. In fact, if you look here, this is our original nucleus. There's absolutely no change in the nucleus except for the energy level and the energy that is being released. The energy can be accounted for in this photon that's being released. All right, I hope this makes sense to you, and I'll talk to you next time. Thanks. Bye.